This is part 2 of the transmission line stuff. So last time we talked about the reflection coefficient at the load, which gives us the ratio of the minus going and plus going waves at the load. And we also talked about the load impedance and how that enforces Ohm's law at the load. Which gives us the ratio between the total voltage and the total current at that location only. But what about at other locations on the line? What if we wanted to know voltage and current at some other position? So we're going to rename gamma a little bit more specifically and name that gamma sub L, the load reflection coefficient. And once again, that, as always, is going to be equal to gamma sub L is ZL minus Z naught over ZL plus Z naught, where ZL is the load impedance and Z naught is the characteristic impedance of our transmission line. So with that out of the way, we do know that voltage as a function of position is equal to V plus, the amplitude of the plus going wave, times e to the minus j beta z plus gamma L e to the minus j, e to the plus j beta z. Sorry about that. Or if you remember that we defined L is equal to minus z, we're going to do everything in terms of L from now on, at least for transmission line stuff. So because this denotes the distance from the load back towards the source. So then if we write the voltage on the line in terms of L, we have V of L is equal to V plus times e to the j beta L plus gamma sub L e to the minus j beta L. There you go. It just flips the sign on there. Now if we factor out the plus going phase component, what we have then is V of L is equal to V plus e to the j beta L times 1 plus gamma L e to the minus 2 j beta L. Now what we're going to do is we are going to define a generalized reflection coefficient that is all this stuff. So now we have a gamma of L, which is the load reflection coefficient times this phase factor, e to the minus 2j beta L. So that gives you the ratio of the plus going and minus going waves anywhere on the line, not just at the load. So gamma as a function of L is equal to reflected voltage component divided by forward going voltage component. And that's true anywhere on the line. So if we were to write that out, that would be V minus e to the minus j beta L over V plus e to the j beta L. So now you see where we get the factor of 2 in the e to the minus 2 j beta L up here. This is important because that generalized reflection coefficient that's what this is called, the generalized reflection coefficient. Accumulates phase twice as fast as the individual forward going or backwards going waves because it's the ratio of the two. So it gets phase coming and going. But that means that now we can write the voltage as V plus e to the j beta L times 1 plus gamma of L. And we can also write the current in a similar way. I of L is equal to V plus over Z naught e to the j beta L times 1 minus gamma of L. So there you go. Generalized reflection coefficient is just another way of writing our voltages and currents and another way of relating them. So now we have the ratio of the plus and minus going waves, voltages or currents anywhere, but we can also get the ratio of the total voltage on the line to the total current on the line as a function of position. And this we give the name Z in, which is called input impedance. So if I use these two equations for V of L and I of L that I just wrote, what I get is that Z in is equal to 1 plus gamma of L over 1 minus gamma of L. That's pretty easy. And it's really easy to do input impedance on the Smith chart. There is a video about how to find the input impedance of a thing on a Smith chart, so watch the Smith chart. Video on input impedance. Ooh, I forgot a very important part there. All right. We can also write the input impedance in another way in terms of the load impedance, the characteristic impedance on the line, and a propagation factor. So we're going to make some substitutions on this equation here. First of all, we're going to use the fact that gamma of L is equal to the load reflection coefficient times e to the minus 2j beta L. Then we're going to use the fact that the load reflection coefficient is equal to ZL minus Z naught over ZL plus Z naught. And then we're also going to write the number 1 as ZL plus Z naught over ZL plus Z naught. We're allowed to do that. We can do whatever we want. So taking these three substitutions and putting them into this equation right here, which I'm not allowed to write that big, what I get is that Z in is equal to Z naught times, here's all the top stuff, Z naught plus ZL plus ZL minus Z naught times e to the minus 2j beta L over Z naught plus ZL minus ZL minus Z naught times e to the minus 2j beta L. So now, if I multiply the top and bottom by e to the j beta L, I get Z in is equal to Z naught times top stuff, Z naught e to the j beta L minus e to the minus j beta L. So that's going to be a sign, plus ZL times e to the j beta L plus e to the minus j beta L. So that's going to be a cosine. Now on the bottom, the sines and cosines get switched which ZL or Z naught they're associated with. So I'm going to have Z naught times e to the j beta L plus e to the minus j beta L. So that's going to be a cosine. Plus ZL e to the j beta L minus e to the minus j beta L. And that's going to be a sine. So remember that cosine beta L is equal to, 2 cosine beta L is equal to e to the j beta L plus e to the minus j beta L. And 2j cosine, that's a sine. sine beta L is equal to e to the j beta L minus e to the minus j beta L. So I'm going to go through and see if I can circle the sines in blue and the cosines in red. So this is going to be a sine, and this is going to be a sine, and this is going to be a cosine, and this is going to be a cosine. So what I'm going to do next is actually divide through by 2 cosine beta L. And then what I get for the input impedance is equal to Z0 times ZL plus J Z0 tangent beta L divided by, oh my goodness, ZL plus J Z0 tangent beta L divided by Z0 plus J ZL tangent beta L. So there you go. That is the expression for input impedance. Now, similarly to that generalized reflection coefficient, rather than having a period of 1 wavelength, this one actually has a period of half a wavelength, because remember that the period of tangent is pi, not 2 pi. And take a look at what happens to this as we move through its periodicity. So if beta L is equal to 0, or some function of pi, or some integer multiple of pi, then tangent beta L is going to go to 0, and then Z in is just going to be ZL. So every half wavelength, the input impedance becomes the load impedance again. So half a wavelength of transmission line is just invisible. Next, if beta L is pi over 2, or n pi plus pi over 2, obviously, then those tangent beta L's go to infinity. So anything that's added to that is going to go away. And so we have Z0 times J Z0 tangent beta L divided by J ZL tangent beta L. The tangents cancel out because they're the same infinity, so that's fine. And then we have Z in is equal to Z0 squared over ZL. Now that's interesting too, because that means that at a quarter wavelength away from your load, the input impedance you see is actually inversely proportional to whatever your load impedance actually was. So let's say that ZL is a short at a distance of 0 or at a distance of half a wavelength, the input impedance